It's
This
been
conference will now be recorded.
for quite a lot of years. Okay, but how can we improve that? How can we, increase the uh, usage of it much more? And how can we, do the R&D for implementing of, charging stations with the help of computer-based tools? Okay, so instead of computer-based tools, not only for creating the circuit as per se, okay, for emulating the the embedded system behind your charging station as well, and how that charging station is going to work. So that is also equally important, right? So yes, so in order to say that, of course, we have separate tool, not separate tool, the same tool, whatever we have used to implement an electrical vehicle component can still be used for power charging station as well, right? So if we have an electrical vehicle, then it is equally important for us to have charging station as well, right? So in order to charge the station as and when we go, like petrol bunks, okay, charging stations is also very important. So how to design them, and what are the tools and techniques which we can use, and what these tools offer us, okay, and how we can do that is what we are going to see today. And of course, renewable energy, everyone is aware of what are the components that are available. Okay, so, so some of the examples of renewable energy is your solar panel, PV module, or your wind turbines. This is more commonly used renewable energy alternative source of fuel. Okay, apart from that, we have tidal energy, geothermal energy. Other things are also there, but we're not going to much focus on that aspects. Okay, how does LabVIEW offer I mean, not lab, I mean, NI based tools, but because we are, focused on NI based tools in order to solve our challenge, right? So what can be used? So before that, we need to understand why we need to have, renewable energy power electronics. Okay, apart from, but to not extract, energy efficiently from renewable energy sources. So if you see, there are different types of, in the solar panel also, we have different types of solar panel, different materials have been used. Okay, so typically it's very important for us to know how to extract the energy efficiently, and how much energy is expected, how much voltage and power is going to expect from individual renewable energy sources. So different renewable energy sources going to supply us with different voltages. Okay, and in order to charge the electrical vehicle, okay, we are going to charge the part of the vehicle that is your battery, traction battery, and the traction battery is going to be on a different level of voltage. So we cannot directly connect your renewable energy source directly to your battery to charge. Okay, it does not work that way. Okay, either the renewable energy source will have a source high voltage and your battery will be of low voltage, or sometimes a renewable energy source will source you very low voltage, I mean very high voltage or very low voltage, and we may need to increase the voltage. We need to boost the voltage to something which can charge your battery. Okay, so two possibilities are there, right? So which means we cannot directly connect the renewable energy source, okay, to your charging station, and from the charging station you cannot connect it directly to your battery. So there must be something, okay, which is going to help us do the transition from renewable energy source to charging your electrical vehicle. Okay, so of course it's not a very complex stuff. So either you're this is going to be pure DC of different level, okay, and the voltage level, your renewable energy source of solar panel, okay, and your battery in your traction vehicle, that is electrical vehicle, is going to require little different type of voltage. Okay, and if you take your wind turbine as a source, okay, it's going to produce variable frequency, AC. Okay, depending on the speed of the rotation, it's going to generate something like that. And in order to convert that to something which can charge your battery, okay, we need to have, of course, again have a converter, power converter. So in order to do that, we are going to use a power electronic, a version of power electronic, renewable energy power electronics, okay, not to convert this source for power sources to something which is can charge the battery. right? So this is well known, okay, to everyone. But our objective is what tools can help us speed up, okay, the development of these tools, development of these products, okay, charging station or battery charger or whatever it is, okay. And of course, yesterday we already spoken about time to concept called time to market. Okay, of course, everyone does research. Okay, everyone brings forward on building the components and buying the components and soldering them together and create a viable product. Okay, but gone are the days where we spend a lot of time. We try to build one version of circuit, and if it is successful, okay, fine. Okay, but we still may try to make a lot of changes. Okay, so in the process, we may damage or we may destroy a lot of prototypes. Okay, so gone are the days where we have to take focus that, because this prototyping, even though it's a good way to do that, okay, it's going to waste a lot of money, capital. Okay, so what nowadays everyone will require to do is, okay, they do simulation. Okay, I mean your computer-based simulation in order to emulate the characteristics of how your circuit is going to work. Okay, so to do that, there should be a viable hardware simulator which is available. Okay, which is nothing but your circuit design platform, right? So of course, I'm not going to say only NI is supplying you with these tools. Okay, there are plenty of other vendors with their own solutions to solve their own problems. Okay, one such vendor, okay, is going to be your NI, okay, which provides us with multisim software. And of course, yesterday we have seen how advantageous multisim was to design the circuit plan, circuit which can emulate the characteristics of it. Okay, then when we want to create a controller circuit for that, we're just going to create an algorithm to control it. Okay, we of course had to go for LabVIEW for the sake, because we need to give some, we need to sequence the flow of the same. So for that reason, we had to go for LabVIEW. Okay, in order to write an efficient algorithm is going to control the sequence at which the inverters are going to switch on, switch off. Similarly, here also we may need to do something like that. Okay, in order to control the power electronic circuits, we may need to have a converter. I mean, a proper, algorithm generator. Okay, so for that we may focus on going for lab, and both together, okay, they can act like handshake both of them together. That is LabVIEW and multisim. Okay, one can act like a plant, and other one can act like a controller. So in this, most of the cases, plant will be your LabVIEW, when plant will be your multisim. Okay, this is basically the circuit, and to control it, we may need to go for lab. Right. So this is what we saw yesterday. Okay, the same way we will use the LabVIEW software and multisim software together with each other to simulate the characteristics of it. Okay, so this is what we have done yesterday. But now the component is how we can simulate the electrical way, I mean the renewable energy component. Okay, so we already seen that there are different types of renewable energy component. That is your what is it? Your renewable energy based solar panel, I mean solar PV module. Okay, you have PV module and you have your wind turbine. Okay, so there must be a way to simulate these components, okay, in your simulation environment, right? So of course, not all the renewable energy components are available as a part. Okay, but fortunately, we have in multisim solar panel model available. Okay, solar panel model with increasing complexity, different complexities are available. Okay, as a component. So using this, we can prototype your solar panel based, controller, renewable energy controller. Okay, for various types of, prototyping of your charging station or anything. Okay, even microgrid inverter also can be easily emulated. So the solar panel, of course, requires us to have some input light intensity. Okay, that can also be fed as a number. Okay, in this case, we have just connected the voltage source to your solar panel. Okay, not to emulate it as 1,000 irradiance. Okay, so based on that, we are going to have some voltage generated off it. A basic model of solar panel. This is available in Multisim. Okay, so using this, we can proceed. So once the solar panel model is available, okay, next we can focus on developing your, control algorithm. Okay, of course, we have different types of control algorithm available. Okay, once you have this PV module, then we can go for a control algorithm, okay, which is going to control your converter. Okay, typically a DC to DC converter in terms of uh, solar panel, okay, PV module, which is going to be acquiring the data. Okay, which is going to the controller is going to acquire voltage and current data from the PV module. Based on that, it will implement this MPPT controller. Okay, MPPT is just an algorithm which is going to track the maximum power available, and until the maximum power is available, okay, it's going to keep on changing the PWM, right? So this is an analysis will be connected to load. Okay, and not always will be the load will be a resistive load. Sometimes it will be a battery load, and battery loads we cannot say okay always it should be connected to maximum power. Okay, most probably for MPPT, for battery charging, okay, we may use same DC to DC converter, but we will fix the voltage at which it will charge, right? So based on the battery type, okay, we'll fix it to go battery charging capability. So how can we create the how can we emulate the MPPT algorithm, and what are the tools, okay, which is required for us to create a model of PV module and DC-DC converter and load. So it's quite obvious that the top portion of this is going to be done using your multisim, okay, because these are components of your electrical circuit or electronic circuit, whatever you call it as, and the bottom portion is basically algorithm implementation, okay, which we need to take a look at. Okay, so getting this feedback from your circuit, okay, your MPPT controller, okay, algorithm will calculate how much PWM it should generate for maximum power generation. So right now we are going to mostly focus on the tool, okay, which we are going to design based. Okay, then we are going to go for algorithm development. So in order to design this, circuit, it's quite in order to create this application, it's quite obvious that we are going to make use of both multisim for circuit schematic design and model creation. So let's see what are our options. So let me open multisim. Okay, and here we have the solar panel model, okay, which is available. And now one might say, if you see here, yeah, I just opened a file and I was just showing you solar panel model. Okay, then but people will be asking, where can I find, okay, in a place a component? Okay, so this component is not available in multisim or like this on how we can find. Okay, if we type solar, we cannot find this component anywhere. Okay, because basically this is an external component which should be downloaded from either manufacturer or from NI website. Okay, so this was downloaded from NI website, and I'm just using it as a template. Okay, so most of the multisim based components either will be provided by the manufacturer itself, okay, or sometimes if you're aware of how we can create spice model, okay, you can create your own model if you know how to program the spice model. Okay, spice model is circuit design, circuit model creation programming, okay, which is supported by LabVIEW, okay, not to create, not to model the circuit. Okay, so it's not really a easy task. Most of the time, we don't focus on that. Okay, we'll just ask the manufacturer to provide us with spice model so that we can just import it inside the development environment and make use of it. So now that we already have this available, okay, let's see how we can give the inputs, required inputs, and harness the usefulness of lab multisim tool. So if you see here, we have this inputs available, okay, for the solar panel model, out of which this is going to be like positive, negative, okay, positive, negative, and here we have this, irradiance input, right? So which can be given as, as a function of number. Okay, unfortunately, we don't have separately as number inside the inside a multisim. Okay, there's no way we can give a numeric input. Okay, any numeric input which needs to be given, okay, will be in terms of voltage, okay, or current, but most of the times it's voltage. Okay, now to check whether multisim, without going for lab view, whether we can just check whether multisim itself can solve this problem. So yes, it should be able to. Okay, when I right click, you can go to place a component, and we go to sources, because that's where we give the voltage current source. And if you see that there's something called signal voltage sources, and here there are plenty of types of power sources. This is power source, and this is where we have this generic AC voltage and DC voltage. Of course, multisim can work with both AC and DC. Okay, but these are fixed voltage source and fixed AC source and fixed DC source. Okay, during the program run, okay, we cannot change anything. Okay, but sometimes we may need to give some interactive inputs and interactive output. Okay, meaning when the simulation is running, we should be able to change the values of voltage or current. So due to that, we have this, signal voltage source and signal current source available. Okay, in that we have different types of voltage source and current source. We have AC voltage source, bipolar voltage source, other not so commonly used sources, out of which we are going to focus on DC interactive voltage. I'm going to make use of this. And if you see, when you move your cursor towards this input and output, you can see that 0 to 10 volts, we can change the values of voltage. And typically, this is going to be the irradiance. Okay, not to give the irradiance, what I'll do is I will double click here. And you can see I can only vary between 0 to 10 volts. Okay, which means 0 to 10 irradiance only we can vary. But typically 0 to 1000 will be an ideal value. Okay, so I'm going to change the maximum value to 1000, which means I can emulate the effects of 0, 1, no, 0, 500 and 1000. Okay, 1000 being the maximum light intensity which can be received. Okay, 0 is going to be like pitch dark. Okay, I can imitate these values as well in the simulation. And increment is basically how much of resolution you can vary. So here I can fix ground, okay, because as we spoke yesterday, ground is very important. So now we have this irradiance based on which the power will be generated by this PV module, and outside will be getting the output. Okay, so in order to measure this output power, I'll just keep a dummy load. Of course, there are plenty of types of load available with which we can work around. I'm going to go for basic. We have resistor. Okay, I'll just basically use a 100 ohm resistor just for the sake of understanding what's happening. So we'll connect it here. So let me just check how it's going to work right now. Okay, I'll just run this run this simulation, and here you can see the simulation is running. Okay, without any flaws, but we need to see how much output power is coming outside. So I'll just use these probes. Okay, I can either use voltage probes across this or current probes to the current, but I have something called as voltage and current probe, which will give me both of them. So here you can see that when I connect to this, you can see that voltage and current probe is available both. Okay, so in order to change this, okay, right now for this much irradiance, we are getting 21 volt across this, and current is going to be basically 210 milliamps, because when 21 volt is maintained across the 100 ohm resistor, okay, that's what's going to happen. Power also, we can just, you can see here, there's the power probe available, which cannot be placed in the wire. Okay, rather we should place on top of the component, just sinking it. So you can see it over there. Right, so when I reduce the irradiance, okay, you can see it will drop at the output also. Right, so that much we can say observe. And of course, this is not like the total power. The MPPT is not still applied yet here. Okay, that's why we can see that even though applying 1000 irradiance, we are getting only 4.41 watts. And of course, this is already configured to be a 50-watt solar panel. How do I say 50-watt solar panel? You can change the characteristics of a solar panel just by double clicking on it. Okay, you'll see something called edit model. And remember, I told you something about a spice model. Okay, so this is the model. Okay, this needs to be written by someone who's aware of this much programming. Okay, they would write a equivalent circuit in terms of programming. Okay, so not everyone will be familiar with this. So in order to prevent the infamiliarity, okay, NI has just provided this formula for us. Okay, then based on the the data sheet of the solar panel, 50-watt solar panel, you can just fill in these parameters. Okay, so when you turn to the back of the solar panel, every solar panel will have these parameters written. Okay, what is the VOC, ISC? Okay, if you have bought a standard solar panel PV module, okay, it's going to have much more complex parameters like voltage constant, current constant, okay, series resistance, and parallel shunt resistance, okay, number of um, solar cells, okay, in series and in division, whatever it is. Okay, so those are given here, right? So I'll just cancel this. Okay, if you want to change the parameters, okay, you have to just consult the proper solar panel and just fill it up. Okay, you don't have to modify anything here because these are all equivalent circuit model of the solar panels is written as a program. This model is created and it's given over here. All right. So now we have a way to bring in the solar panel inside the lab view, I mean, inside the NI ecosystem of Multisim. Okay, similarly, we should be able to create our own power line circuits to implement a controller, okay, MPPT controller or whatever it is, it's worthy of creating, we can create it. And that requires us to have some power electronics implementation. Right, so the algorithm implementation, of course, it's going to be different types of algorithm out there. Okay, previously people were using perturb and observe, incremental observe, and incremental conductance. Okay, based on this, they will change the duty cycle slowly over a period of time. Okay, until that until the power settles down at maximum. Okay, if it is not changing, okay, then if it starts to reduce, okay, then the people will just fix it at that portion. Okay, will keep on tracking. So perturb and observe is basically like we'll keep on changing the duty cycle, okay, until it's going to settle down. So we'll be seeing a demo on these two algorithms, okay, on how to make use of the implemented portion. But the important part is how to implement the circuit and how to implement the algorithm behind it and how to validate. So of course, we already brought in the component of solar panel. Now we need to build the circuit inside the power electronic circuit inside the multisim as a part of MPPT based charging station. Okay, since renewable energy is used, we need to implement the maximum power point tracking system. Okay, which is basically going to monitor and control the output power from the solar panel. Okay, not extract maximum because on its own, okay, renewable energy cannot extract maximum. Okay, one of the reason being it's a variable power source, and the components involved in the renewable is also not going to be very um, very direct portion. So one such implementation is for MPPT is there should be a renewable based power electronic circuit in between. Okay, not to convert the power from directly from renewable energy source to something which can charge the battery. So that circuit, it could be a DC-DC converter, it could be a DC-DC converter, mostly DC-DC converter if it's a DC based renewable energy source. Okay, or it's going to be a AC to DC converter. Okay, so if it's a AC based renewable energy source like that wind turbine. So of course, either buck converter can be used or a boost converter can be used. Okay, for implementation sake, let's just go for buck converter based MPPT. Okay, so this circuit is taken for convenience for us to build it. Okay, it's a synchronous buck converter. Okay, which makes use of two MOSFETs for switching purpose, right? So in order to instead of using an extra diode, okay, in order to reduce increase the efficiency of the switching of the buck converter, okay, people will use two instead of having a not to avoid the drop due to diode. Okay, we will use an extra MOSFET. Okay, and both of the MOSFETs are complementary, as you can see. Okay, when this is on, this will be off, and this is off when this will be on, like that. And the controlling part is typically, if you want to do this both total MPPT controller, okay, so we need to go for multisim lab eco simulation, okay, which will be staying in short duration. But let's start building the circuit, okay, in the multisim. So we already have your solar panel here. So now we just need to make use of MPPT algorithm and the circuits involved in implementing that we brought inside the environment. So of course, if you have any questions, please do let me know in the comment section. I'll routinely check it and answer your queries. So here we are going to make use of, create a buck converter. Okay, values have been already selected for purpose. So the calculation of values, we can basically refer a proper, reference tool to do that. Okay, there are plenty of tools available as a reference. Okay, now to change the values of your inductance and capacitance, which plays a very dominant role. Okay, apart from that, the MOSFET also, which is going to be based mostly on output voltage and output current, and also input voltage and input current. Both of them should be considered. Okay, more importantly, switching frequency of the boost converter is going to be very instrumental. Okay, in selecting those. Okay, we need to make sure that the switching frequency of the buck converter or boost converter is not going to go beyond RF. Okay, so if you go beyond RF, it should be a power MOSFET which is capable of switching at RF frequencies. Okay, so we need to be very careful in that. And of course, we have a lot of web-based tools, okay, which offers us to, when we enter certain parameters, it's going to suggest us an appropriate buck converter. Okay. So I thought I had a question. Fine. So just give me a moment. Yeah. Yes. So yesterday we saw that in order to generate the waveforms, in order to generate the inputs for your inverter, we directly gave from LabVIEW to here. Okay, but not all frequencies controls will be supported by from LabVIEW. Okay, sometimes for simulation, we need to make use of multisim based sources for PWM generation. Okay, and yes, we do have certain sources available in multisim in order for us to do the just that. Okay, so what do we have? So here we have the solar panel. Okay, next we have to focus on getting the solar panel controller in the MOSFET, and of course we all know where we can find an appropriate MOSFET. Okay, the place component, of course. So I'll go for all groups. So when you know the value, when you know the part number of the component, you can just try searching for them here. So for me, I know IRF 520 is a MOSFET, okay, which I'm going to use. So it's a 100 volt 9.7 ampere MOSFET, okay, which seems to be okay for me. Okay, I'll just make use of it. Since it's a synchronous boost, buck converter, I'm just going to use two of them. As soon as I place it again, I can replace it. So I have two copies. And next is going to be a Schottky diode. Okay, the diode component. So for Schottky diode also, I know the part number, but if you want to find it manually, you can always go to diodes. Okay, there's a section for diodes. You can see that there's a Schottky diode available. And if you can scroll somewhere over here, you'll find the component, but I'm not going to search for it manually. Okay, as a matter of fact, we have something like 1162 Schottky diodes, which will be very inefficient for us to search manually. Okay, NBRV1045G is the component which I require. So I select it and it's working. And next component is going to be inductor. Inductors are pretty much basically a basic component. So you can select basic, and here you'll find resistor, capacitor, inductor, out of which I'll select inductor. And according to the design component, okay, we require 33 microhenry inductor. So 33U, if you enter it, will ask us whether it's 33U. I can select it. I can click over here. And next one is going to be the capacitor. Capacitor also basic. Capacitor. Hundred microfarad, 100U. And we can place it here. We need one more capacitor, one more diode, in order to prevent the black flow of current from battery to if you're using a battery, okay, in order to prevent the reverse flow of voltage, okay, from load to this source, okay, we need to have a diode. And of course after that a load. Base component. And here right now for our sake, okay, I'm just going to go to resistor load. Suppose placing a component is first. Just a moment. Okay. Yeah, sorry. Yeah. So now we just need to interconnect them. So this goes here. Okay, so then after that, this goes over here. And ultimately we'll finish it off. So we have this over here. But now next is going to be controlling of your MOSFETs. Okay, we have the source here, we have our load ready here. Okay, and next is going to be your MOSFET controlling. Right, so MOSFET control, it's not like I mean as same as how we control the MOSFET of your inverter. Okay, actually in inverter also we had to do an extra step, but since it was simulation I didn't do it. But here in this simulation that should be done. Okay, last time when we supplied the voltage from LabVIEW to multisim, LabVIEW to the MOSFET, okay, that whatever voltage I gave to your gate was with respect to ground. Okay, but typically it wasn't able to source the total 12 volts. Okay, so normally what we have to do is we need to have a isolated voltage source, okay, like a driver, okay, which should force the voltage which is always supplied with respect to ground is something just generated with respect to source. Okay, so in order to do that we need to make use of something like controlled voltage source. Okay, controlled voltage source will act like a driver here for simulation purpose. But in real world, of course, we need certain appropriate MOSFET driving strategies like a bootstrap circuit or optocoupler, something like that we have to make use of. Okay, drivers, appropriate driver circuit should be used. Simulation purpose, we do have these components. Okay, so yeah, as a simulation component, but it will slow down the simulation if you use more components. Okay, or else you have to have a faster computer which will make which will make it possible for us to simulate. Okay, right now my computer is not that much fast, so I'm just going to avoid doing that. So I would rather use a controlled voltage source as a driver. Okay, so I'll make this up a voltage controlled voltage source available here. Only one component because the other MOSFET, the source is anyway connected to ground only. So whatever voltage we give with respect to source. But this one, we should have an isolated component is like voltage control voltage source, which will generate voltage at this gate with respect to source. Right? And this could be connected to ground. And this is almost done. So simulating this, okay, you could do this like for your inverter, we have to create a custom sequence on our own. Okay, different sequences we were able to create. Okay, but for a DC to DC converter, normally PWM is what we have to generate, right? So that could be generated basically by in the multisim itself. Okay, so PWM is available as a component. Okay, in place component, we can find PWM as one of the components. Okay, so multisim is built as one of the important reasons why multisim was built is for power electronics emulation. Okay, so out of all these generic components like basic components, diode, transistors, in transistor we have this MOSFET available. Apart from that, you can see that there is something called as power components. In power also we have these switches available. Okay, IGBT, along with thermal model also is available. Modeling for a component is also available. Okay, we also have like SMPS model components, power modules, okay, which is available here. And what we're going to focus here is we're going to use a power controller. And there you go. You see something called as phase angle controller if you want to do AC to DC converter. AC to DC controller. Okay, we have single phase controller, three phase, two phase, two pulse controller, six pulse controller for three phase. You name it. Okay, and of course, we also have a PWM generator for inverter control. Okay, or a single for, let's say, DC to DC converter. We also have for three phase inverter as well. Okay, SPWM generator is also available inside the lab view itself, inside the multisim itself. And what we require is, since it's a synchronous, okay, we need PWM which is complementary to each other. So we'll go for something like a PWM complementary. Instead of only one output, we'll have a complementary output also. That's the only reason. This and this is going to be complementary with each other. So one input will be given here, and the other one will be given over here. And of course, we need to configure this. They are going to ask us how much frequency this is going to generate. Okay, during the design, I believe we asked for 30 kilohertz frequency. Okay, 30 or 50, I'm not sure. Okay, I think it's 50 kilohertz of frequency. Okay, based on that only you had your inductor and capacitor selected. Also your MOSFET as well. And how much output voltage does it require? Okay, so the PWM which is going to be generated, typically the embedded system is going to generate it. It's not going to generate that much frequency, that much voltage. So of course a driver will be required. But this, since it's simulation, I'm going to have this PWM generator generate the gate source voltage, which is typically required for us to turn on and turn off your MOSFET. Okay, it is 15 volts. Okay, this is going to be one. So basically, reference minimum, signal minimum, and reference signal maximum is going to help us scale how to scale between 0% duty cycle and 100% duty cycle. Okay, if you give input a 0 voltage, okay, it's going to generate 0% duty cycle. Okay, it's like a reference voltage, okay, which will map. 0 is equal to 0%, 1 is equal to 100%. Anything in between, like 0.5, if you apply, it will generate 50% duty cycle. Okay, and the output is going to be the output voltage amplitude of this PWM, which is going to be the turn on turn off voltage of your MOSFET. So the hundreds of ways how I can make the simulation do. Okay, I can bring this inside LabVIEW and I can control this, or I can do the simulation LabVIEW multisim itself, but mostly open source only, open loop only. Okay, meaning I can just change the PWM and output is going to change with respect to voltage or current. Okay, but if you want to do closed loop, okay, if you say go stand at 12 volts or 13 volts, okay, and it should automatically adjust itself. Okay, if you want to create a closed loop, you probably have to go for LabVIEW to implement closed loop system. Okay, now I'll just select sources, signal voltage source, and I'll have this DC interactive voltage source again. In order to change the duty cycle, of course. So this voltage input is going to be the duty cycle input. Maximum is going to be 1, minimum is going to be 0. Okay, I'm going to have increment of 1%. So 0 to 100% I can change with increments of 1. and I can observe the voltage input and output at both, you know. Okay, I've forgotten this capacitor. And of course, I can connect this from here to here, but it will not look neat. So I'll have one more ground here. And this is voltage at, sorry, voltage and current at input. And voltage and current at load side. Sign up this program. And you can see that it's slowly going to rise. And you can see the duty cycle is 0.5, meaning the input output is going to be half the size of input. Okay, so how the buck converter works. Okay, so we are applying 21.1 and here we have 10.3. Okay, so it should be 10.5, but considering the components available here, the drop will be there. Okay, but if I increase it, it's going to, again, it's going to increase. Okay, it's going to be almost same. Okay, but of course, there's going to be a drop. But this is going to act like a buck converter. But this is a good way to implement it, yes, of course. Okay, but sometimes we will say, okay, I need to have my output voltage as, um, 13 volts to charge my 12-volt battery, let's say. Okay, this is showing us 14 volts or 13 volts or whatever it is. Okay, let's say I change it to 13 volts. Okay, my battery is charging properly. This is ideal when my illuminance, that is my irradiance, is constant. But here we are talking about renewable energy and we are talking about sun. Okay, for solar plant, and always in a solar plant, your irradiance is going to change. Okay, and when the irradiance changes for this given duty cycle, the output voltage will also change. Input voltage also change, output voltage will also change. So you can see that it's changing. Okay, slowly it's coming down. So in that case, open loop is not really going to be very effective. Okay, in order for us to implement the charging station. Okay, until the power is available, okay, your charging station should be able to extract the power, right? So in that case, you need to have of course an MPPT controller, which is nothing but a closed loop system. Okay, so to do that, of course, for just checking the circuit out, this is good. Okay, but ultimately we need to go for uh, lab view. So components like this value and this value, irradiance and voltage, okay, needs to be given from lab view. Okay, so where do we give it then? I'll move this here. I go place. connectors, core simulation terminals, voltage input terminal. Okay, we'll control this duty cycle from lab. And for various irradiance values, we will just give it from lab itself. So again, we'll create a connector between lab and core simulation. Okay, again, input voltage and output voltage also needs to be observed. So for observing voltage, we do have a voltage input terminal, voltage output terminal, but we don't have a current output terminal to measure the current. Okay, we have V input. We also have V output as well. But how do we measure I output and I current in the I input? So it's not really a challenge. We just need to convert voltage to current to voltage. So for that, we have a component in multisim called as current clamp. It's going to act like a current clamp DMM. It's going to convert the voltage to current for us. So you can see there is a conversion factor. 1 volt is going to be equal to 1 milliampere. I just use a 1 millivolt to 1 milliampere, which is going to be equal to 1 volt per 1 ampere. I'm going to have two components of it. One is at input and one is at output. And this is going to be again a voltage output terminal. I input and I output. Right? So now this must be brought inside multisim for further progress and for lab view. Okay, so I close this. Okay, and to implement the MPPT algorithm, okay, we can go for lab view. Okay, of course, there are different types of MPPT algorithm. Okay, you can also implement a PWM based for charge controlling. Okay, basically for battery charging, okay, we need to fix it at a appropriate voltage. So voltage, okay, instead of trying to extract maximum power. Okay, so for that we need to have a PID. You can also use a PID based controller. Okay, for that, an appropriate way to do that is by using your lab view. So yesterday we have seen that in order to extract, in order to bring the multisim inside lab view, we have to make use of a simulation toolkit, something called as control and simulation tool. And here we can extract model, external model, and we'll have the multisim design model. I browse, I will bring desktop, I will have this solar model. You can see these inputs are available here. So since LabVIEW is a graphical programming tool, okay, the control in Multisim, even though it was possible, it was not really a user-friendly way to control it. Okay, you can see that in LabVIEW we can create our own virtual GUI with drag and drop methodology. So here I can name it as duty cycle. Okay, it should vary from 0 to 1. And here it's basically irradiance value. For that also I can create a knob or dial or whatever it is very comfortable for us. So by varying these two things, either by open loop or closed loop, we should be able to do the control. So we can just create an indicator in LabVIEW to view the outputs. Or as yesterday we saw, there was a way for us to visualize these outputs values. So how do we do that? So we have this toolkit available here in LabVIEW, the simulation toolkit, which enables us to visualize data in a good format. Okay, in the form of waveform chart. And we can see here, and in this program, let us save it before. So saving in desktop as MPPT model. Here run this. So you can see that there is some sort of perturbation is happening. Okay, we're not sure what value is which. So I'll stop this and I'll just map it with it. Okay, first value is V in, second value is V out, third value is I in, and fourth value is I out. Okay, and instead of having all these things in one scale, I can right click, I can stack plots such that each and every one of the values is going to be in different stuff plot. Yeah, as you can see. So first one is V in, second one is V out, third one is I in, fourth one is I out. I save again. I increase the radians to 1000 and then this program again. So if duty cycle is 0, of course, it's that there's nothing going to be coming outside. Okay, of course, input voltage will be there, but output will still be in terms of microvolts. And of course, obviously, again, reduce to 0. Let me just increase the duty cycle and see. If you see here, it's going to rise up. Right? So we have to change the duty cycle to adjust the output voltage. So that's how a normal buck converter also works. Okay, it's not a which is proper. But we can make this closed loop, of course, obviously. Okay, by making use of a appropriate closed loop mechanism, that is, you can build an MPPT algorithm, okay, by using the lab use programming, expertise. Okay, that also you can do. Okay, so that requires a lot of time for us to build it. Okay, or we can use an existing open loop controllers, closed loop controllers, okay, like PID algorithms, in order to enforce this closed loop system. Okay, so for a closed loop, basically I can make use of a PID controller which is available. I have this control simulation. If you see, I have this PID available, which I can make use of. So for which I have to give the set point. Okay, process variable is nothing but the current voltage, current value. Set point is nothing but it's nothing but where it has to be. Okay, so that values are given here, and ultimately you have to basically need to tune the PID properly. Okay, because PID, of course, it requires a lot of tuning and stuff. So we have appropriate VIs in order to may help us tune, which you can make use of obviously. So yeah, we have this I out available, V out available, which is going to be our set point setting. Yeah, process variable is no more, it's not going to be duty cycle. Rather, I'm going to have a battery charging voltage. This ideally battery charging capability. So it will be available over here. And output range is nothing but it's going to be like this, 0 to 100. Okay, I'm going to prevent this from exceeding the voltage. Okay, so even though I said something like 30 or 40, okay, so this should not go above that. Okay, I'll set it as 40 and 30. I mean 20 and 10. And ideally this should be connected here, but I cannot directly connect the output of this PID function as an input of duty cycle. We need to convert this output to to a function of duty cycle. Okay, and since this is buck converted, it's pretty much easy. We need to just divide. This is the function of voltage and this is the function of duty cycle. Okay, and we have a formula which we can convert this voltage to duty cycle. Okay, we have V naught, we have Vs. Okay, this is V in. Okay, so V naught by V in, and V in by V naught, when V naught by V is going to be your duty cycle, right? So that's what we are going to do. We are going to divide and we are just going to connect it. It will break because it's like in the same iteration we cannot connect the output to input. So we need to add a delay, okay, in the value. So of course we do have a delay here. In simulation utilities, we have this memory available. So one extra iteration after the data will go. So I'll have a initial value, something like this. So now instead of giving in terms of duty cycle, I will have a battery charging voltage, which I can use a digital display, and I can say I need this to be in 12 volts or 13 volts, whatever it is. I save it, I run it. So of course we need to fine tune it. Okay, we need to set the proper values. There are a lot of solvers available which we may need to use. So probably something is wrong with the one version I built. Okay, well, the same thing I built here. Okay, with certain other modifications. So along with PID gains also is altered. So if I run this, it's going to go and settle at this given voltage. So it's going to take some time to settle down, obviously, but at up for a certain point, you can see that it's going to go settle at the given voltage. So if we say 14, it's going to go arrange itself, adjust itself to go and settle down at 14. This is a PID based charge controller. Fine. So if your objective is on building, extracting maximum power, okay, instead of for charging station, okay, you can also build the same using a boost converter. Okay, so I'm not going to build this right now, obviously. Okay, so there is already a built version, so which was tested by using the traditional MPPT algorithms like perturb and observe and incremental conductance. Okay, which was built using LabVIEW. Okay, it's nothing but the implementation of this, you know, flow chart. Okay, which when you run, okay, it's going to give you certain values as output. So IPV should be divided by 1000. So if you see per term and observe, it's just going to keep on increase, decrease, increase, decrease, increase, decrease. Due to the disturbance, it will keep on. It will not settle at the upper values. Incremental conductance, on the other hand, so it's going to be more defined if you see. So code has been developed in LabVIEW. It's not going to have that much of disturbance here in incremental conductance. So yes, these are tools available inside the NIN ecosystem. Okay, of course, apart from that, if you want to go for implementation purpose, then you want to go for like already we have developed much of the code. Okay, in the simulation algorithms, we have controlled the control your simulation model. Next is basically utilize this code, use this code to control LabVIEW uh, you know compatible hardware by just replacing the input and output to multisim with input and output to hardware. Okay, so that implementation is not really hard, to be honest. Okay, there are plenty of support examples available inside. So you can see that there is a FPGA based program available, okay, which can implement the same, and making use of that we can develop it. So yes, that's from my side. If you have any questions, please do let me know. Okay, I'll be glad to help you out. My contact, as I've already shared, is over here. I'll post it in the comment section. But any questions, please let me know right now also. So along with tracking, okay, they have made a program which is going to control an FPGA, okay, inside the Rio hardware and bring it for us. So any questions so far, please let me know.
I think when they practice, they will get so many doubts, sir. It is difficult to ask questions now. Hello, dear participants. Any queries?
So in that case, I would like to thank everyone for attending my session. So I'm available for contact via this contact details which I have presented to you. So with which you can reach me out and let me know. So there are ample of opportunities. This is one such domain with which you can solve engineering problems using the NI tools. But there are plenty of other possible potential modes which LabVIEW can be used to solve apart from electrical vehicle based problems. Okay, so there are ample of opportunities. Okay, so if you're interested to discuss, okay, surely you can contact me. So thank you everyone. I'll conclude my session right now in that case.
Good evening, everyone. Thank you, sir. Thank you for accepting our invitation and spending this much time to give hands-on experience for our participants. So if it happens practically, it will be very nice. But still, the sessions to both sessions are very good. And participants they're also practicing and they are requesting for the sample files, sir, from you. Yesterday, some of the participants they kept personal messages for me. At least sample files. That means you demonstrated in the session those files they are requesting for, and the PPT also.
Okay.
So if they have that one, it will be helpful to practice more. That means if they have any doubts, they can clarify.
Sure. I'll just through my management, I'll just share it with us, so it will be beneficial for everyone.
Okay, sir. Thank you, sir. Thank you very much, sir.
Thank you everyone. So yeah.
Dear participants, again we will meet on tomorrow at 10 a.m. Thank you everyone. And validatory, we are not planning any separate session. At the end of the last session, we'll be having basic feedback session. Okay, it is not listening validatory. That means we won't speak. You need to speak regarding the workshop. You need to give feedback regarding the workshop in the last session for 15 minutes. And then at 6 o'clock, we will be having examination. Okay, dear participants, thank you everyone. We will meet again on tomorrow.
Thank you, madam.